Suppose we have a matrix. If we interchange the rows and columns of this matrix, we will get a new matrix. This is called the transpose operation. This matrix is called the transpose of the first matrix. To understand this, let's find the transpose of matrix A as shown. Let the matrix that we obtain after transposing A be B. Let's see how we obtain this matrix. The first row of matrix A becomes the first column of the matrix B. Similarly, the second row of A becomes the second column of B. Now, the completed matrix is the transpose of A. The transpose of a matrix A is denoted as shown. An alternate representation of the matrix is written as A superscript T, where T denotes the transpose. It should be noted that the order of the matrices is of importance. If the order of the original matrix is m by n, then the transpose is of the order n by m. Now, we can define the transpose of a matrix. If A be an m by n matrix, then the matrix obtained by interchanging the rows and columns of A is called the transpose of A. Now, we discuss some properties of transpose of matrices. We will now verify these properties with the help of examples. According to the first property, the transpose of a matrix is equal to the matrix itself. We will verify this with the matrix X. Let's find the transpose of X. Next, we will take the transpose of X. We observe that it is equal to X. The second property states that the transpose of the product of a matrix and a constant is equal to the transpose of the matrix multiplied by the constant. Let's verify this using the matrix Y by finding the left-hand side. We multiply Y by a constant, 5. Next, we will take the transpose of this matrix. Now, we find the right-hand side by taking the transpose of Y. Then, we multiply this matrix by 5. You can observe that the left-hand side is equal to the right-hand side. The third property states that the transpose of the sum of two matrices is equal to the sum of the transpose of matrices. First, we will find the left-hand side of the relation. The sum of matrices X and Y is as shown. Now, we will take the transpose of the matrix. Next, we will find the right-hand side by adding X transpose and Y transpose. We can see that the left-hand side is equal to the right-hand side. We will verify the fourth property by taking the matrices as shown. Let's find the left-hand side. First, by finding the product of matrices X and Y. Now, we will take the transpose of matrix AB. Next, we will find the right-hand side. First, we will find the transpose of matrices X and Y. The product of Y transpose and X transpose is as shown. You can see that both the sides are equal to each other. Based upon the transpose operation of a matrix, we can observe some properties of matrices. Suppose we have a matrix as shown. Let's find the transpose of the matrix. We can observe that the transpose of the matrix is the same as the original matrix. We can say that X is a symmetric matrix. We can now define a symmetric matrix. A square matrix A is said to be a symmetric matrix if its transpose is equal to itself. Let's observe another property associated with the transpose of a matrix. Let's find the transpose of the matrix, shown here. We can observe that the transpose is equal to the negative of the matrix. In this case, Y is called a skew symmetric matrix. A square matrix is said to be a skew symmetric matrix if its transpose is equal to the negative of itself. Consider the two matrices. Now, for any element in Y, the corresponding element in Y transpose is of negative value. We can observe that any element Aij in Y is equal to minus Aij in Y transpose. If I is equal to J, then we have Aii is equal to minus Aii. Therefore, we have 2 Aii is equal to 0, or Aii is equal to 0. It means that all the diagonal elements in a skew symmetric matrix are equal to 0. This is evident in matrix Y. Next, we will see two theorems based on symmetric matrices and skew symmetric matrices. The first theorem states that for any given square matrix A with real number entries, the sum of A and A transpose is a symmetric matrix, and A minus A transpose is a skew symmetric matrix. A is a square matrix with real numbers as its elements. For the moment, let X be the sum of matrices A and A transpose. If X is a symmetric matrix, then X is equal to X transpose. Let's substitute A plus A transpose in place of X in X transpose. Using the properties we have seen earlier for transpose of a matrix, we can see that the right-hand side can be represented as shown. This implies the right-hand side is equal to A transpose plus A. This indeed is equal to X. Therefore, X is a symmetric matrix, or A plus A transpose is a symmetric matrix. Similarly, we can prove that A minus A transpose is a skew symmetric matrix. Let us denote this matrix with Y. If Y is a skew symmetric matrix, then Y transpose is equal to the negative of matrix Y. Let's substitute A minus A transpose in place of Y in Y transpose. Using the properties we have seen earlier for the transpose of a matrix, we get A transpose minus A. Upon rearrangement, we find that this is equal to the negative of matrix Y. Therefore, Y or A minus A transpose is a skew symmetric matrix. Let's verify the theorem with an example by using matrix A as shown. The transpose of A is also shown. First, let's verify whether A plus A transpose is a symmetric matrix. The matrix A plus A transpose is as shown. If we take transpose of this matrix, we find this equal to the matrix A plus A transpose, which verifies the first part of the theorem. Next, we will verify that A minus A transpose is a skew-symmetric matrix. Let's take the transpose of the matrix. We can observe that the transposed matrix is the negative of A minus A transpose, which verifies the second part of the theorem. The second theorem states that any square matrix can be expressed as the sum of a symmetric and a skew-symmetric matrix. Let A be a square matrix with real numbers as its elements. From the previous theorem, we know that A plus A transpose is a symmetric matrix, and that A minus A transpose is a skew-symmetric matrix. We will multiply each of these matrices by 1 upon 2 and add them. We will use the property shown here to simplify the sum of the matrices. Hence, the theorem is proved.